Let us begin. All right, so come and grab a book, Louis. Guys, before we start the topic of inducing an EMF for things like generators and creating electrical energy from mechanical energy, we need to understand the topic of flux. Okay, now flux is a measure of a field that's passing through a given area. Again, we can visualize it with field lines, okay? But it turns out this idea of magnetic flux is important. Then we can jump to the change in magnetic flux, because it's the change that's occurring which is going to do all of the fun stuff. But let's start with our basics. So let me just bring out my notes on magnetic flux. So imagine we have a coil, a rectangular coil, as is shown in the diagram. Obviously there would be wires leading in and wires leading out, but for this simple diagram, just treat it as a rectangular coil. If you have your field lines traveling through, you'll notice that we have an area and a magnetic field strength. Okay. As we start to rotate that coil, the perpendicular area begins to decrease. Now I'm going to try and show you what the perpendicular area is as best I can. It's going to be sort of this region underneath. The best way to think about it is the shadow of the coil, the shadow of the area as we rotate. So if I said, imagine that the magnetic field lines are the rays of light that are traveling from the ceiling. And right now my coil is such that you've got the biggest shadow, all right? Now, as you start to rotate your coil, that shadow is going to start to decrease. And then when you get to a 90-degree rotation, there is no shadow. Okay, so there is no perpendicular area. And we would say, well, there's no flux because there is no magnetic field passing through the area because there is no area. So the only way you get maximum field lines passing through that area when the field is directly perpendicular, when the plane of the coil is directly perpendicular to the field. Now, in order for us to get a nice equation, I want us to bring in the idea of the normal, which is the orthogonal vector that points straight out from the plane of your coil. Now, you're probably familiar with the normal when we do inclined planes and reaction forces and things like that. So, let's get to this section here. We have the symbol for flux is phi, and it equals B A perp. And we will say that A perp is going to be A cos theta. And so we get flux is BA cos theta. But we need to make sure we have our theta understood. Theta is the angle between the normal and I'm going to say normal to the plane, and the direction of the field. So we'll put that in a box.
This angle will always equal the kind of...
Well, it can only be 90, it'll vary from 90 to 0.
Yeah, but it'll always be the angle between the plane and kind of the shadow.
Yes.
Yeah.
Yes. So you can see in my diagram. Let's look at the first diagram. Let's have an example. Let's say that we have 100 millitesla magnetic field going up in this diagram. And let's just for the time being say that this is 10 centimeters by 10 centimeters. So that's 0.1 squared, which would be 0.01 meters squared. Okay? You can see we've got maximum flux in this scenario. Because it is directly perpendicular, you could say that the angle between the normal and the field equals 0. And so we could calculate, we could quantify, it's going to be BA cos theta. We'll go 0.1 by 0.01 cos of 0. Cosine of 0 gives us a maximum value, it gives us 1. And we would get 0.001. Now let's look at the units. We can simply take the units from what we've multiplied. Magnetic field strength, Tesla. Multiplied by area, that's meters squared. However, there is another unit, and that is the Weber. Capital W, lowercase b. The Weber. It's capitalized because it was named, again, after some German dude. Okay. Now, I also want to include, and I probably put that arrow too soon, flux does have a direction. This is important because we need to, if we're looking at how the magnetic flux changes over time, we've got to say in what direction is it changing. So we've got to go, all right, in this diagram, we'll just go with the direction of the field to our normal, okay? And so we'll say upwards. Okay, we'll say 1 Weber equals 1 Tesla meters squared. I mean, units. Get rid of the 1, doesn't matter. So a Tesla meter squared is not really sort of any useful kind of unit for us. It'll make more sense as we go along. Now let's, as I said, consider now the example of the light with the shadow. If I've rotated my coil by 25 degrees, now the angle between the normal and the field is not 0, it's now 25 degrees. So all we need to do is multiply by cosine of 25. So let's just go theta equals 25 degrees. We'll go our flux equals BA cos theta. And so we'll take that same value and we'll reduce it by cos 25, which is 0.906. And so we get 0.000906 Weber upwards.
25 degrees, right?
No, we'll still go with upwards because the direction of the direction of the field. The direction of the field relative to...
So you're doing the magnitude of the norm that is parallel to the field?
Yes, that, upwards. Cool. It's still upwards, but it's been reduced because we're now rotating that coil around. So that's fine. We could go 9.06 by 10 to the negative 4 Weber, or we could go 0.906 milliweber upwards. They're all correct. They're all good. Okay. All right. Now, I'm hoping that you still have some room on this page, because that's pretty much it for flux. BA, done. That's easy. You just find the perpendicular distance, and there might be some Weber questions. Probably not, but we'll slowly go through it. Have a look at what's happened. We've gone from a milliweber up to 0.9 milliweber up. There has been a change in the magnetic flux. What is the change?
What's 0.001 minus that?
Yes, but in what direction? Down. Good. I want you to try and treat it as a vector. It's like saying if I was traveling 1 meter per second north and then I changed my velocity to 0.906 meters per second north, what is my change in velocity? Well, you go final minus initial, you would get negative I'm bad at maths, 0.094 south. So the change is in the opposite direction. If it was going up and it's slowed down, the change is down. Okay? Now, what this involves is a convention. So I might say over here, convention, up is positive, down is negative. I mean, we're pretty cluey with that since year 10, just adding simple displacement vectors. So I could now go that the change in flux is final minus initial. Remember, anytime we have a delta, it's final minus initial. Delta T, delta S, delta B, delta V, whatever vector you want to look at the change in. All right, so let's just quickly write this in. We're going to go plus 0.906 minus plus 1, milli Weber, gives negative, what was it, 0.094. Okay. So we've jumped straight into some pretty heavy stuff. Flux is BA cos theta, but then we want to consider initial and final. So I could sort of add, initial here, final there. We rotated it from that position to that position. So I could go flux initial and flux final. Doesn't matter. I'm just suggesting that we went from that to that. Okay. Could we please go over the page? A circular loop of radius 10 centimeter is placed in that field, as shown. Determine the initial flux. Okay, so now we've got to kind of set a normal here. Let's say that the normal is in the same direction as the field. I'm going to say that my flux is directed into the field because we're looking at a magnetic field B that's going into the field. All right. So let's just go. All right. B is 0.1. The area of a circle is pi r squared. Cos of 0. So again, we can't really see the normal because the normal is either going to be coming straight out of the plane, straight out of the page, or straight into the page. Okay. Here's the thing. It doesn't matter which way you set it. You're either going to get cos of 0 or cos of 180. It's kind of like setting your convention. If I set my convention as into the page, then I have to stick with it. It's like the kid in year 10 that decides to be cocky and go, I'm going to set north as negative and south as positive. Well, if you set that convention, you have to stick with it. It doesn't matter because at the end, you're going to use your convention to figure out the direction for your answer. All right, so throw it into your calculator, you get 3.14 times 10 to the negative 3. Or 3.14 milliweber. That's fine. Whatever. Oh, and it's into the page. Okay. Now, I'm going to force the convention over here because I screenshotted that diagram and I put it into your booklets. I want you to use the convention for this page that if you're into the page, that's a positive value, and if it's out of the page, it's a negative value. Okay? So we could then go, well, if we want to convert this to maths, it's going to be plus 3.14 milliweber. For the sake of mathematics, we can convert direction into plus. Yeah, remember, do not ever leave your final answer as plus or minus. We have to provide a direction. Okay. Now, if we were to suddenly, we don't know what's producing this magnetic field. Maybe it's a set of coils that, using the right grip rule, blah, blah, blah. In that, where that coil is, it's in an external field. All right, let's turn that field off. It's now 0. Okay? Now, before we start, just off to the side, I want to show you that there's a few different ways to get a change in flux. Basically, you could change the magnetic field. So that would be delta B times A cos theta, which is what we're doing in this first example. In which case we could write B final minus B initial. That's one way to change the magnetic flux. We could increase the field strength, we could decrease the field strength, we could turn it on, we could turn it off. The next one is we could change the area of the coil. So that would be B delta A cos theta. Now it's a bit hard to visualize changing the area, but imagine that I had a little collar on my coil, and imagine I grabbed that collar and I sort of pulled one wire like a shoestring, like a noose. If I could pull that wire down, the area of that coil is going to decrease. That is also one way to change the magnetic flux. You're going from a large flux into the page to a small flux into the page. The change in flux would be out of the page. Okay, so imagine that. Or you could go the other way. You could pull the wire upwards, and that would increase the area of your coil. Then we're going from a small flux into the page to a big flux into the page. The change would be into the page. So that's another way to get a change in flux. Let me just quickly expand that. That would be a constant B outside of A final minus A initial cos theta. And then lastly, the final way would be B A delta cos theta. I could change the angle of the normal to the coil. On my diagram, that would be taking my coil and rotating it around, get it spinning. So if I took that coil and I rotated it by 90 degrees, it's going from some flux value to 0. That's the physics behind a generator. You're taking a coil and you're rotating it around in a magnetic field. That's how you can change the flux. So there's 3 different ways. You can change the field, you can change the area perpendicular, or you can change the angle of the coil. Let me just quickly write B A bracket cos theta final minus cos theta initial. So just those are the 3 ways to change flux. Okay. All right. So let's determine the change in flux if we were to turn off the field. So delta flux. Flux. Oh boy. Delta flux. I wonder what the automated annotation feature would say about all of my fluxes. We're going to go, what's changing? It's delta B outside of A cos theta, which is B final minus B initial. So let's throw it in. Well, final is 0 minus, now I set my convention at the start that's positive. Then we can throw in our area, which was pi. Oh, hang on. Wait. Crap. Try again. What was B? B was...
So you can just subtract the
0 point... Yeah, I know, but I want to just keep it all here. So we'll go 0.1. So there's my change in magnetic field. The convention still works. The change in the magnetic field is going to be negative, which is now out of the page. Then I'll throw in my pi by 0.1 squared cos of 0. So yeah, as you rightly said, that whole term is just simply going to be negative 3.14. So we can say 3.14 milliweber out of page. I don't know why I'm shouting, but there we go. Okay. All right. Now, I'll give you a quick little... You're going to do exactly the same here, but imagine as instead of turning off the field, we change the direction of the field. So instead of 100 millitesla into the page, we somehow, I don't know, maybe what's producing that magnetic field is on some kind of alternating current that's going to produce an alternating direction of field. Maybe it goes from into the page to out of the page. So you're going to do exactly the same mathematics, but now your B final is going to be what? Negative 0.1. Okay? So do the following, please. Negative 0.1 in your delta B.
Do you need to write B final minus initial, or is just delta B okay?
I would
Well, you're right.
show all of you working out. Showing all of you working. Show all of you working out. There is one other method. You could go flux final minus flux initial.
Yeah.
And what you'll get is negative 3.14 minus positive 3.1. You get negative 6.28. That's the answer. I just get the answer. 6.28. But there's going to be two different ways to get to it. So do that same step. But if our field is reversed, we're going to say B final equals negative 0.1 Tesla. And as I said, I mean, many of you, I can tell you guys are pretty cluey. You should be able to look at that and just, you could shout out the answer without writing a single thing down. But I need you to, use the mathematics. Okay? So the direction is still the same. The change in direction is still out of the page, but the magnitude is doubled. Think driving a car. If you're traveling north and you stop, your change is south. But if you're driving north, you stop, you clutch in, you chuck it in reverse, and then you do a sweep rollback and start reversing back to travel south, your change is still south, but then obviously the magnitude is doubled, because you've gone from a certain speed forwards to the same speed backwards. Okay? Don't do that, you'll burn out your clutch. Bad for the car. All right. Now, some of you have already started the next question, which is fantastic. Let's now look at, now we're going to rotate the coil by 60 degrees. So have a just quick think. Theta initial is 0, theta final is 60. We're going to reduce our flux by the cosine of 60. So we're going to take this one, chuck him down here. Okay? So we'll go change in flux is BA cos theta initial, try again, cos theta final. So 0.1 pi by 0.1 squared. And you can do this all in your calculator in one step, and I'm hoping you'll get a negative value. Yes, Callum?
Quick question. When it is rotated about its axis by 60 degrees, is it clockwise or anti-clockwise?
It shouldn't matter. So our axis of rotation is...
Yeah.
Well, later on in the course, we will figure out rotating it one way will produce a certain change, rotating it the other will produce a certain change. But for now, the change is still going to be out of the page. Still. So go cos of 0 minus cos 60. And what do we get? 1.57? Negative 1.57.
What if 10 to milliweber?
What? That's right.
It doesn't
Oh,
actually matter.
sorry, okay. Sorry, I stuffed up. Yep. Final minus initial. Cos 60 minus cos 0.
So it doesn't actually matter because cos 60 is a half. So you're going to end up with...
Well, you know, the previous one would have given a positive value.
Yeah.
So we need the negative. So yes, thank you. I had it the wrong way. That would have been gaining flux. That would have been going back the other way. So 1.57 milliweber out of page. Okay. Yes, Brownie.
I'm just wondering with the equation with the delta, why is it delta cos theta and not cos delta theta?
Because you're... Well, I'm going to answer that by forcing you to do this all again. In just a moment, I'm going to ask you to do flux final minus flux initial. And I'd like you to do BA cos theta minus BA cos theta. If you look at it like that, then it's delta cos theta, not cos delta theta. So that's very different mathematics. Guys, last question down here. Who's already finished it? You guys are working. Charlie, you done it? Get going. Last one is the final way of changing. That would be changing your area. So we can say B cos theta outside of A final minus A initial. This is a tricky one where you don't really have a convention for area, because area is scalar. So this one's not really going to help us with the convention. It turns out it gives us a negative because it's reducing. Oh, maybe it does. So what's final? That's pi of 0.05 squared minus So it just so happens that all of these changes that I've chose for this page, they're all reducing the flux, and so the change is going to be in the opposite. So in every single scenario, it was out of the page. Okay, so maybe if I was better prepared, I could have increased the flux for one of these scenarios. Now, what I want you guys to do in sort of the last... Do we have any room? Maybe on the front page. I'd like you now, for these last two questions, to do what I was explaining to Brownie about do the entire flux final and minus the entire flux initial. So it's pretty much different mathematics, but you're going to come out with the same answer. But I just want you guys to confirm with yourselves that you've got two options for any question. You can either do the entire flux, subtract the entire flux, or you can separate what's changing. It's literally just a common factor. You're factorizing out the constants on the left-hand side, whereas what I want you guys to do now is to keep it all So that's going to be BA cos theta final. Put it outside the... Okay. And if you're lucky, one of those terms might go to 0, and you'll still get the same value. So can you do that for me now, Ben D'Souza? Do you have any... Oh, what? No, you haven't. Oh, you're not showing enough. That's very neat. Where's this value come? Oh, it's up there. Yeah, I see. Well, you can just sit there smug for 10 minutes. You see if there's any questions that we could look at.
So do we have things like induction?
Yes. But before we look at it, we've got to get good at delta flux. Okay. No, I don't have any questions. Now these values, final minus initials and minus. Would somebody mind telling me what the the final flux was? It'll be a bit smaller. Oh, it's a half. Is it a half? Is cos 60 a half?
Yeah.
Okay, so it's going to be...
Quite a lot. Like on the calculator online.
If you're just be careful. Yep, you can solve them all separately, write them down, then wipe your calculator. Yep, but by doing that, you're adding an extra step, an extra chance of making an error. So you just got to be careful that you're tapping away and putting in brackets correctly. Okay. Oh, this one's going to suck as well. What's this one going to be? Somebody help. What's the final flux when the coil radius is halved? Thank you. Okay. Cool. All right, guys. I'm going to give you another question, and I want you to think, and I want you to discuss it with your partner, and I want you to give me the answer in just a moment. Palaline.
Which direction?
So which way up or down?
Let's go right. So we're going to have the uniform magnetic field of 0.5 Tesla right. So how would you draw this? You could almost go, here's my square coil, and here's my magnetic field. All right? So that's what I'd like you to consider. Oh, now hang on, I've got to make sure I don't give you an impossible question. Hold the phone. All right, so we're at 3.3 is measured to be... All right, boom. Makes you think, doesn't it? This is still this is a reduction in flux again. I should have. Has anyone written the word left yet? I'm changing my mind. Let's. No, because that if it's left, then there's 3 options. If it's right, then there's only 2 possible solutions. Let's go with 3 possibles. Chat amongst yourselves. Figure out the answers. Have a think. On the previous page, there were 3 things that we could do. There's going to be 3 things that we could do. Calm down, Wilson. Shot of adrenaline so early in the morning.
The current's going that really forced that way.
Either rotate or you could make it smaller.
You are. Or we could.
Yeah. That'd be the easiest one, I think, because then you've just got one.
Now, obviously, how.
Coil. It's changing the magnetic field.
Oh, cathode.
Isn't it say we can only change the coil?
Well, you could also rotate it. Because we're reducing it. We're at maximum flux right now. Yeah?
We can rotate it and I can make it smaller, but we can't change the magnetic field.
Yes, you can.
It's
Oh.
not the coil though.
Pretend that you can. I had to say the word uniform so that we in here, but pretend that it's a variable uniform. It's a uniform field that can vary. Yeah? Oh, countless.
Always been.
Space to do it 3 times.
Yeah, I should have. Next year I'll do it on the front page. On the back page. So, guys, this one, it's almost working backwards. You've got your delta is known and your initial is known. You've got to solve for the final and change one variable so that it works. But you also need convention. If we said that right is positive, then our delta is negative. So I'll give you a quick little, I don't want to force the convention, but if we say right is positive, then the change has to be negative.
Sir,
All right?
sir, if you could theoretically run a current through this coil, would it then not produce a force that would rotate and decrease the surface area and how many flux lines pass through?
So, as we will learn, generating electricity is the opposite of a motor. With a motor, you have electricity in a magnetic field produces mechanical energy. We're going in reverse. We have mechanical energy rotating a coil in a magnetic field. It will produce the electric potential. You're 3 lessons ahead, maybe 4. Just get this question done.
What's bad issue?
Plus 0.150.